Okay, so for this video, be sure that you've printed out the examples so that you can follow through. The examples have a lot more information on them. They basically serve as some extra notes to supplement the PowerPoints. Here I'm just going to go over the solutions to the examples on the example sheet. Okay, so we're talking about the sampling distribution of the sample proportion. And again, we're treating the sample proportion as a variable because from one sample to the next sample, it's going to obtain different values. All right, so we want to figure out how is it distributed, when can we say it's normal, and then when it is normal, we want to be able to analyze and find some probabilities. So example 1, the proportion of SUNY Broome students that take a mathematics course in the fall semester is 0.38. Describe the sampling distribution of the sample proportion of SUNY Broome students taking a math course for samples of size 50. And as a note here, there are approximately 6,000 BCC students. Okay. So just like with the sample mean, there's a few things we want to do, three, in these cases. Is the distribution of our sample proportion normal? Then what's the mean and the standard deviation? Now, we want to check for normal here by taking n times p times 1 minus p and seeing if that's greater than or equal to 10. If it is, then the shape of the distribution is going to be pretty close to normal. All right, so n, the sample size, is 150 times p, 0.38. Right, p is the notation for the population proportion, so we know that to be 0.38 here. Then 1 minus 0.38 would be 0.62. Again, we're asking ourselves if that's greater than or equal to 10. I'm just going to punch this up on the calculator. It's going to be bigger. It's 35.34. Definitely greater than or equal to 10. So that lets me say the sample proportion all right, p hat is the symbol that you're going to see for the sample proportion, is normal, with mean, same type of notation, mu for the population mean. It's the mean of the variable p hat, so p hat is the subscript. That's going to be equal to the true population proportion. And then finally, the standard deviation sigma, p hat is a subscript. This one looks a little bit sloppy. It's p times 1 minus p over n, all inside a square root. So here, you know, if the directions say write it as a decimal, I'll write it as a decimal and round it off. But in a lot of cases, you're okay leaving it like this. So the one reason you might want to leave it like that is later on if we need to do calculations with it, this will make sure that it's in exact form and it'll match anything a book or solution manual gives us. If you are going to turn it into a decimal, at least initially give a whole bunch of decimal places. Even if your final answer to whatever question it's going to be is rounded off to the nearest tenth or hundredth, if you write this standard deviation as a decimal, show a bunch of digits. Okay, so again, here is a complete answer to one of those sampling distribution prompts. We've stated that it's normal and we've given its mean and its standard deviation. That is a full description of what the sampling distribution is. Here we want to work with that same scenario for example 2. It says going back to the same scenario in example 1, if we collected a random sample of 150 BCC students, find the probability that the sample proportion of students taking math is more than 0.40. I'm going to take the same approach as I did for the sampling distribution of the sample mean. It's just that the notation for standard deviation of the proportion is different here. So we're still going to say, well, we've got a normal distribution. The mean we said was 0.38. Now we're trying to find the probability that our sample proportion, which is a normal variable, is more than 0.40. So that's going to look like a 0.4. And we're doing an area to the right. Here's where you can leave it up to you. If we do this in everything exact, I'm going to have my 0.4 minus my mean of 0.38. At this point, if you want to turn the standard deviation of your sample proportion, this thing up here, if you want to turn this into a decimal, go ahead and just show a lot of decimal digits. If you would rather leave it in exact form, that's okay too. Either way, you'll be okay, but if you do turn it into a decimal, show a bunch of digits. All right, when I punch this up on my calculator, if you're going to keep it exact, on the calculator, throw parentheses around the numerator. When you hit divided by and open the square root, it'll open up a set of parentheses. This is just a string of multiplication in division, if you want, in square root. So you can really just punch in 0.38 times 0.62 divided by 150 and then end the parenthesis. And then that should give you this in one step. And if we do this out, again, I'll ask you to check me. Easy to hit a one button wrong. If we punch this out in the calculator, I'm ending up with rounded off 0.50 for the z-score. Now we're going to go to the table to find the area to the right. And again, it's going to appear blurry on this format, but we're using table 5, the normal areas. Our z-score is 0.50, so I would look at 0.5, and I would go to the value in this first column because the hundredths place is 0. And a little bit hard to read, but I think it's 0.6915. Remember that table area, though, is the area to the left of the z-score you looked up. We want 1 minus that table area to find the area to the right. So our answer to this problem would be 0.3085 is the probability that in our sample of 150 BCC students, we get sample proportion of more than 0.4, which means more than 40% of our sampled BCC students were taking a math course. All right, so in this process, right there, just like with the sample means, that's what you got to watch out for. You got to remember we're using the normal approach because we have a normal variable. So we're doing our normal approach, but we got to remember to use the standard deviation for our sample proportion. If you can remember to do those two things, you're going to be just fine doing these problems. Okay, let's take a look at another scenario. This one, you know, if you want to kind of make a asterisk, because this one would be harder. Students tend to struggle more with these kinds of questions, so I definitely wanted to take a look at one of them. Suppose a manufacturer just received a lot of 60,000 parts needed for their manufacturing, and suppose 4% of the parts are defective. A quality control specialist selects a sample of 600 parts, and the protocol is to reject the entire lot if more than 12 of the sampled parts are defective. What is the probability that the engineer accepts the lot? Okay, so I guess the first thing here is we got to know what they're asking us for. So the way that I kind of think about this is this is kind of asking me to find the probability. Now, the probability that the engineer accepts the lot would be the probability that there are less than, well, that there are 12 or fewer defective parts out of the 600 sampled. So find the probability that p hat, our sample proportion, is less than or equal to 12 defects out of 600 sampled parts, which if you turn that into a decimal, that's 2%, so 0.02. So we're being asked to find the probability that our sample proportion is less than or equal to 0.02. Now we know that our population proportion is 4%, or 0.04. And if we have sampled 600 of these parts, it's pretty much guaranteed, except for really, wacky scenarios, that you've got yourself a normal distribution. If you tried to do that p, or the n times p times 1 minus p, right? N is 600, p is 0.04. That means 1 minus p is going to be 0.96. If we multiply those together, I'm getting 23 point something, 23.04, I think. So I'm going to put a check because that's greater than or equal to 10. Remember, that's the cutoff. So that tells me it's normal. Now, one of the other things the book comments on, but they don't really seem to ask you a lot specifically in the homework, but I want to comment on it here, and I'll go back to the previous example, is in general, you want no more than 5% of the population to be sampled. The reason for that is if you sample more than 5%, then the probability that an individual shows the characteristic, whether it's a defect or whether it's taking a math class, changes along the way because you are removing a lot of individuals from the population. So here, sampling 600 out of 60,000, if you punch that up, that's 0.01 or 1%. So we're certainly fine as far as being under 5%. So if you read through the text and you see the 5%, that's what they're talking about. They generally want to make sure that less than 5% or 5% or fewer of the population is being sampled. In the previous problem, where it says, note there are approximately 6,000 BCC students, they're probably telling us that because our sample size is 150. If I take 150 and divide it by the 6,000, that's going to be less than 5% also. In fact, I think that comes out to 2.5%. So that's, one of the general guidelines, just to make sure that you can basically assume that along the way of sampling, your probability of obtaining the characteristic stays the same. Okay, so we have a normal scenario here. I'm just going to make a note that my sample proportion p hat is normal. Remember, we know that because we checked the n times p times 1 minus p. The mean of the variable p hat is going to be 4% because that was the population proportion. And the standard deviation is going to be the square root of p times 1 minus p over n. So again, we have a normal variable. And if I go back to my original thought here, we're trying to find the probability that our sample proportion is less than or equal to 0.2, because we wanted to find the probability that the engineer accepts the lot, and the lot would be rejected if there are more than 12 defective, so that means it would be accepted if there are 12 or fewer. All right, so we did the 12 over 600 to get the 0.02 cutoff. So we want to try to find the probability that our sample proportion is less than or equal to 0.02. 0.04 is the mean. This standard deviation is a really small value, so I'm going to put my 0.02 way over here because I think that's going to be several standard deviations below the mean. Again, if you want to take this expression right here and right now convert it into a decimal, that's fine. Just list a whole bunch of decimal places. For whatever reason, I tend to just leave it exact. Now you want to make sure you practice punching these into the calculator, because when these expressions get more complex like this, it's more and more likely that careless, button pressing issues are going to creep in. All right, so when we punch this out, I'm getting a z-score of negative 2.50. Now we wanted the area to the left, right, because we were going to accept this if there were 12 or fewer defects, which means 2% defective or less, which is convenient because when I look up negative 2.50 in the table as a z-score, the table area would give me the area to the left, which means I'm done with the problem. So I'm getting 0.0062. But as always, check the table, make sure I didn't read a number wrong. And again, these problems, there's a few tricks to them, using the correct standard deviation, applying the normal approach. And as you can probably see, some of them are definitely trickier than others. So see how the homework problems go. Send me messages when you get stuck. And good luck, everybody. Have a good day.